Hi, welcome to Thinking from First Principles. Examples. Okay, so here we're going to look at two examples of solving a problem from what Elon Musk refers to as first principles. This video is a sequel to the video, The First Principles Method. What is Elon Musk talking about? So you might want to check out that video first if you haven't watched it already, before continuing here. So Elon Musk attributes a lot of his success to something called reasoning from first principles, and he also points to a physics education as a way to acquire these skills. In describing his problem-solving method, he has said that framework was developed by physicists to figure out counterintuitive things. So here we're going to do two examples. And in our first example, we'll look at one of those counterintuitive things the physicists figured out. In our second example, we'll apply the same methods to a very practical, everyday type of scenario. Okay, so Elon Musk described reasoning from first principles by contrasting it with what he called reasoning by analogy. So let's look at those two things. Okay, so let's say you're going to solve a problem. Reasoning by analogy would have you do the following. You look for a similar problem that has already been solved. Then you take the solution to that problem and tweak it to fit your situation. And now let's look at what first principles would say. So basically, you question your assumptions until you get down to fundamental truths, or at least things that you're pretty sure are true. And then, starting from those axioms, you build a solution to your problem. So we're going to start with an example from physics where reasoning by analogy fails very badly. So we're going to look at the energy levels of the hydrogen atom. So don't worry if you don't understand the physics. What we want to concentrate on here is the process of questioning assumptions, figuring out what our axioms are, and then building a solution to the problem. Okay, so example 1, energy levels of the hydrogen atom. Now, we should mention a few things about this example. So this example is standard material that would show up in, say, an undergraduate class in quantum mechanics. We're going to concentrate on how a physics student might approach this problem today. We're not going to spend too much time on how it was solved originally, but we will come back to the historical development a little bit at the end of the example. The hydrogen atom consists of a negatively charged electron and a positively charged proton. The potential seen by the electron is proportional to minus e squared over r, where r is the distance between the electron and the proton, and e is the charge of the electron. Now, it turns out that the electron can absorb or radiate light. And when that happens, the photon has an energy, E, that is given by h nu. Now here, h is what is known as Planck's constant, and nu is the frequency of the light. Now it turns out that the photon energy only takes on extremely specific values. And this hints to us that the electron has specific energy levels. And so the photon energy is equal to the difference in energy between two of these levels. So when an electron changes from one level to another, it can do so by either absorbing or radiating light. So here's our goal. We want to explain this, and we want to calculate the possible electron energies in the hydrogen atom. Okay, so let's try to solve this problem. First, let's try reasoning by analogy. So, the problem that we want to solve is that we want to find the energy levels of the hydrogen atom, where we just saw that the electron is in a potential that is proportional to -1/r. There's an obvious analog in Newtonian mechanics, specifically a planet orbiting the sun. So in this planetary system, we have, say, the Earth, rotating around the sun at a distance r, and here also the Earth is in a potential that is proportional to -1/r. However, if you try this, a couple of very serious problems arise. First of all, classically, a revolving charged electron will radiate light, it will lose energy, and it will spiral into the nucleus, the proton of the hydrogen atom. So this predicts that the atom wouldn't even be stable. And second of all, the classical examples like the planetary system didn't even have energy levels to begin with. So here, reasoning by analogy gets you absolutely nowhere. Okay, so now let's try the first principles approach. Let's start by questioning our assumptions. So the planetary system example was non-relativistic and classical. Here, by non-relativistic, I mean that the effects of relativity, specifically special relativity, can be ignored. And when I say classical, that means that quantum effects can be ignored. So we have to ask the question, do these conditions hold for the hydrogen atom? Okay, so let's look at each one of these in turn. First, let's ask, is the system non-relativistic? So in order to answer this question, we're going to do a back-of-the-envelope calculation of the type that a physicist would do in order to figure out if the electron was non-relativistic or if we have to include the effects of special relativity in our calculation. So we said before that the energies of the photons that are radiated by the electron are of order 1 to 10 electron volts. This energy is much, much less than the rest energy of the electron, which is equal to the mass of the electron, me, times c squared. This tells us that the hydrogen atom system is very likely to be non-relativistic. Okay, so if none of what I just said made any sense, that's totally fine. Here's the take-home message. So in the planetary system example, we don't have to take into account the effects of special relativity. We want to know if the same is true in the hydrogen atom example that we're trying to solve. In physics, we have a rule of thumb that tells us whether or not we have to take into account the effects of special relativity. Here, I've applied that rule of thumb and found that we do not have to take into account the effects of special relativity. So in this respect, the hydrogen atom acts just like the planetary system. So the assumption that we can ignore the effects of special relativity is A-OK. Okay, next, let's question our other assumption. Can the hydrogen atom, like the planetary system, be treated using classical mechanics, or do we have to include quantum effects? In quantum mechanics, we have something which you might have heard of, the Heisenberg uncertainty principle. It tells us that the uncertainty on the momentum of an object, here denoted p, times the uncertainty on that object's position, here denoted x, is greater than h bar over 2, where h bar is Planck's constant divided by 2 pi. In units of electron volts meters divided by the speed of light c, this is 9.9 times 10 to the minus 8. While quantum mechanics tells us that delta p delta x is greater than h bar over 2, If delta p delta x is anywhere near h bar over 2, quantum effects are likely to be important. So let's do a rough estimate of delta p delta x. We said that the energy of the electron changes by an amount of order 10 electron volts. Let's take the non-relativistic expression for kinetic energy and say that delta E is approximately delta P squared divided by 2 me, where again me is the mass of the electron. Taking delta E to be about 10 electron volts gives us that delta P is about 3000 eV over c. Now let's take delta X to be the approximate size of the atom, 1 angstrom or 10 to the minus 10 meters. Multiplying those together, we get that delta P delta X is around 3 times 10 to the minus 7 electron volts meters over c, which is about 3 times h bar over 2. This is not much larger than h bar over 2, so this tells us that quantum effects cannot be ignored. Okay, so again, if none of that made any sense, that's perfectly fine. Let's just look at the take-home message. So in physics, we have a rule of thumb that tells us whether or not we can treat a problem classically or whether we have to include the effects of quantum mechanics. Here, we've applied that rule of thumb, and we've found that for the hydrogen atom, unlike the planetary system, we have to include the effects of quantum mechanics. So our assumption that we carry over from the planetary system, that this is a classical system, is not okay. Okay, so let's look again at what we've done here. We questioned our assumptions and found the following. We found that the hydrogen atom system is non-relativistic, just like the planetary system example, but it is outside the realm of classical physics, unlike the planetary system example. So, since it's non-relativistic and we have to include quantum effects, that means we need non-relativistic quantum mechanics. So, we're going to take the laws of non-relativistic quantum mechanics as our first principles. Now, we use those first principles to build a solution to our problem. Okay, so we're going to take the fundamental relation of quantum mechanics, the Schrodinger equation. Specifically, what we've written down here is the time-independent Schrodinger equation. So in the Schrodinger equation, we can see a wave function psi, an energy E, which is what we want to solve for, and V, which is the potential that we've seen before. So we take the Schrodinger equation and we insert the correct expression for V so that it's proportional to minus 1 over r. And we then solve this equation. We get the solutions for the wave functions psi and their energies E. And if you do this, this does in fact agree with experiment. Additionally, you can also generalize this to other atoms, and if you want to be more precise, you can include relativistic corrections, etc. Okay, so we've seen here that for the hydrogen atom example, reasoning by analogy fails dramatically. But first principles reasoning leads to a solution that is in agreement with observation. Reasoning from first principles helps when solving fundamentally new problems, and the hydrogen atom was definitely fundamentally different from the planetary system. And it's important to note that the eventual solution may be completely different from how we initially look at the problem. So here we ended up having to solve a quantum mechanical system, whereas we might have initially thought that we were looking at something that looks like the Earth going around the sun. Okay, so what we've seen here is how we would approach the problem today, for example in a class in quantum mechanics. We questioned our assumptions, we ascertained what set of rules applied to this problem, and then we took those rules, which happened to be non-relativistic quantum mechanics, as our first principles, and then we applied those principles to get a solution. So this example is a really good illustration of the difference between reasoning by analogy and reasoning from first principles. Now, this is a pedagogical example, but in research, the situation is likely not going to be so straightforward. So it may be less clear just how many assumptions you have to question, and if your initial attempt at a solution fails, you might have to start over, questioning deeper assumptions as you go. And you may even have to come up with new first principles that you haven't seen before. So since the process in research is usually less straightforward than what you see in an example in, say, a quantum mechanics class, it might not be so surprising that the actual history of understanding the energy levels in the hydrogen atom is a bit messier than what we just went through. So absorption lines in light from the sun were first observed in the early 1800s, but Rydberg and Balmer first started writing down empirical formulas for the wavelengths of the absorbed light quite a bit later in the 1880s. And the Schrodinger equation, which is what we just used in order to solve this problem, actually wasn't formulated until the 1920s. And that didn't happen until after other developments had already happened in quantum theory. Okay, so now let's go on to a completely different example. Example 2. Too much furniture, too little space. So this example is going to be exceedingly ordinary. It's going to be about a scenario where you probably wouldn't pay too much attention to your decision-making process. But we want to use it to illustrate 2 points. First, you likely already use the first principles method of solving problems, at least a little bit. And second, unlike in the physics example, the first principles are not necessarily set in stone. They depend on the problem, and they may depend on the priorities of the person who is trying to solve that problem. Okay, so let's look at our scenario. A person shows up at the beginning of the academic year at a university that they are attending. They're going to live in university housing, but the information about the housing that they were given was incorrect. So the place is only half the size that they were told it would be. So they have way more stuff that can easily fit in the new place. So, faced with this unexpected situation, the question they ask themselves is this: what do I do with my things so I can live in my new place? They start by trying to rearrange the furniture to find a solution. And this might fall under Musk's reasoning by analogy. Rearranging the furniture fails terribly. So, they start questioning their assumptions. So they ask themselves the following questions. 1. Can I live somewhere else? 2. Do I need to keep all of these things? 3. Can some of the items be replaced by smaller things, or things that are multi-purpose? 4. Of the things I need, do they all need to be here? And 5. Can the effective amount of space in this place be increased? So let's look at how 3 different people would proceed in this situation. Each one of them is going to question their assumptions, figure out what their first principles are, and then build the solution from those first principles. Okay, so let's start with person A. Person A has no time or money to move to another place to live. They need all of their stuff for school and work, and all of their items are used on a regular basis. But they are handy with tools, and they really like to build stuff. So let's see how they would answer each of these questions. So, can I live somewhere else? No, they don't have the time or energy to move. Second, do I need all of these things? Yes, they need all of the items for work or school. Can these items be replaced with smaller or multi-purpose things? Again, no. They need all of these items for work or school. Do the necessary items need to be here? Again, yes. Can the effective amount of space be increased? Well, since they're handy with tools, they say that the answer to this question is yes. So, here are the first principles for person A. They must live in this place. They must have all of their stuff, or almost all of their stuff, on the premises, but they have skills to alter the living space. Here's a possible solution consistent with their first principles. They could build new storage. They could build a loft space to move many of the items off the floor. And in fact, in order to design this new loft space, in fact, they've come up with a new problem to solve. Okay, now let's look at person B. So person B is a returning student. They do not wish to move to another place. They have a sentimental attachment to all of their belongings, so they refuse to permanently get rid of any of them. But they have many items that, except for sentimental reasons, aren't really used, and they're just kept in storage boxes. Also, person B has no building skills. So, let's see how person B answers each one of these questions. Can I live somewhere else? No, they're not willing to move. Do I need all of these things? Yes, they're sentimentally attached to all of the items. Can the items be replaced with smaller or multi-purpose things? No, because they have a sentimental attachment to all of their things. Do the necessary items need to be here? Well, technically, no. They want to own these items, but they don't use them all the time. So they don't actually have to be on the premises. And can the effective amount of space be increased? Well, they've decided that they are not good at building things, so they're going to say no. Okay, so what are the first principles for person B? They must live in this place. They must keep all of their stuff, but not necessarily here. And they will not be altering the living space. So here are some possible solutions consistent with their first principles. They could rent an off-site storage locker. Or they could lend unused items to friends on the condition that those items will be returned at some point in the future. Okay, now let's look at person C. Person C is a new student. They don't know anyone at the university. They want to solve this problem with spending as little money as they possibly can. They can't afford a larger place. But they do have stuff that they don't need. And they, like person B, have no building skills. So let's see how person C answers these questions. Can I live somewhere else? No, I can't afford to. Do I need all of these things? No, actually. Can items be replaced with smaller or multi-purpose things? We're going to go with no, because that would probably involve spending money. Do the necessary items need to be here? Yes, because they can't afford storage and they don't yet have any friends in the area that they could loan items to. Can the effective amount of space be increased? No. Okay, so here are the first principles for person C. They must live in this place, but they can get rid of some stuff, but anything they keep must stay on the premises, and they will not be altering the living space. So, a possible solution consistent with the first principles of person C is to throw out or give away, or if they want to get a little bit of extra money, sell unneeded items. Okay, so we've looked at how these three different people would solve the problem. But we could also imagine scenarios where it would make sense for a person to move to a larger place, or it would make sense to replace some of their belongings with smaller versions or with multi-purpose items. But basically, different scenarios will lead to different solutions. Okay, so there are two lessons that I would like to emphasize here from example 2. So lesson 1. You probably already reason from first principles, at least to some extent. So there was nothing particularly mysterious about the way persons A, B, and C solved this problem. But they questioned their initial assumptions, determined what characteristics they required their solution to have, and then they built solutions fulfilling those requirements. Okay, and lesson 2. The first principles are not necessarily unique. So here, the solutions shown depended upon the priorities of the person who was solving the problem. This is very different than what we saw in the case of the hydrogen atom, where the first principles came from the laws of quantum mechanics. Okay, so at this point, we've seen two very different examples of solving problems by reasoning from first principles. Let's look at what lessons we have learned. In both examples, we saw that you question assumptions until you get to a set of principles that you're not going to budge on. Those principles might be laws of nature, or they might just be your priorities. Okay, so next. Your eventual solution may look nothing like the original formulation of the problem. We saw that in both of the examples in this video. In example 2, person A started by rearranging their furniture, and they ended up designing and building a storage loft for their new apartment. And as an entertaining example, Elon Musk initially tried to buy a rocket, and then when that didn't work out, that's when he decided to try building them. Next, for hard problems, you may have to iteratively question your assumptions. And for truly original situations, you may have to formulate new first principles. And lastly, and perhaps most importantly, it's important to realize that you likely already reason from first principles, to some extent, when solving problems in your everyday life.